Good morning all. I'm Litan Mandari from Indian Institute of Technology, Roorkee, India. So this work was done by my colleague Mr. Additively, but he was unable to attend this conference due to some reason, so I'm presenting on behalf of him. So the topic is a study on fatigue damage in additively manufactured inconel 718 alloy. So most of the part of this presentation is focused towards experiment, but also we have done some simulation work to validate some results. Yeah. So coming to the additive manufacturing, as we all know, it's an emerging field. So it's a process of joining material from three-dimensional model data, usually layer upon layer. So it got various advantages, like it can provide us design freedom. It can optimize the time fabrication. Also, it's combine the component with the assemblies, and also it got some limitation as well, like defects. So it has process-induced defects and limitation on the size of the component. So it basically depends upon the size of the bed. And then we selected few objective. We evaluated the characteristics of IN718 alloy used for SLM. Then we investigated the light fatigue property of SLM fabricated IN718 alloy. Then we investigated the microstructure and mechanical properties of heat treated as well as fabricated inconel 718 alloy. Then we modeled this process using FE solver, means Abacus, and validate few results. So basically we have used Renishaw AM400 machine for the fabrication of this alloy. So initially we have some powder, IN718 powder, which is procured from Renishaw, and we used this AM400 machine to fabricate few samples, that is fatigue as well as tensile samples. And like initial as fabricated sample of higher tensile residual stress, then we did some heat treatment to relieve the residual stress. So this and the process, the parameter will already optimized. So we have used the optimized process parameter, and the build layer was 30 micron. So we printed one layer of 30 micron. Then again we have printed 30. Similarly, we fabricated this sample in horizontal direction. Now, this is like somewhat chemical analysis and size distribution of powder. So I'll skip this one. So basically, the mean diameter is 32 micron. The diameter of this mean diameter of this powder is 32 micron, and this is the chemical composition. So then we have selected three different material conditions. One is the as fabricated, and second is the heat treated, that is the stress relieving heat treatment. Then the third is we have fabricated the sample, then we have machined that sample. So yes. Then a cube is also printed of 10 by 10 by 10, and we have polished this one, and we observed the melt pool boundary. So the main focus of this presentation is to validate this one, and also we did the fatigue analysis in that case. So the initial microstructure is cellular and the columnar dendritic near to the melt pool, and we also observed the needle-like structure, which is the delta phase. Yes, this is the part of UVSD analysis. Basically, you see like the grains are oriented towards the building direction. This is my building direction, and the grains are elongated to the building direction on the side faces, and you can see some sort of equivex in the top surface. Then again, we did the tensile analysis of three specimens, three material condition. That is the as built. As built is your black one, which is having higher ductility and lower strength. As we increase the heat, we did the heat treatment, the strength drastically improved in the expense of ductility, and this as machined, which is intermediate between the two. Then we perform the high cycle fatigue analysis on the same specimen at three conditions, like heat treated, as built, machine, and as fabricated. So we got endurance limit, the fatigue limit of 200 in as built case. So this 10⁻⁷ denotes the number of cycles that it ran. So we selected this as a time life. Then as built machine have a life of 300 ampere, whereas in case of heat treated, the life has improved, and they have a endurance limit of 400 ampere in that case. Also, we evaluated the mean stress effect. As we know that mean stress affect the fatigue life as well. In that case, we did at two different R ratio, that is 0.1. The R ratio is the stress ratio, so we did at two different stress ratio, 0.1 and 0.5. In case of 0.1, we obtain a fatigue limit of 250 MPa, and in case of 0.5, we got a limit of 185 MPa. So these all the tests have been done at room temperature at a frequency of 10 Hz. Then we did some low cycle fatigue behavior analysis. So this our material shows some hardening behavior. So I will skip this one. So we have three different strain we have selected in that case. Yes. Now coming to the damage analysis of the fracture specimen. The fracture specimen were analyzed using scanning electron microscope to observe the crack in different zones where how our crack has been initiated. So in most of the cases the crack has been initiated from the defects. So that includes like unmelted powder particle, porosity, even lack of fusion. Those are the few defects from where the crack has initiated. And this shows the propagation zone. Then propagation zone have few significant features like striation field observed, and few more defects like laser spatter has been observed. Now coming to the analysis part, FEM analysis part. So this is the full flow part. We basically selected one substrate of steel and we printed of IN718, and we used the material property that we obtained from experimental, and few material property we selected from few literature. So that's temperature dependent, I'll explain later. Then we used the deflux subroutine to model the Gaussian heat source, and again to see the phase change effect we have used user defined field. These are the basically boundary conditions. We selected the initial boundary and temperature condition to be at room temperature at 298 Kelvin, and the heat transfer between the component and environment that occurs through condension and adhesion. So it can be represented by this equation. Yeah. Now these are the input parameter that we have used in our setup, and the time dependent some properties we have taken from the literature. So you see like laser power we have already used 270 watts. So we have selected these are our parameter that we have used to fabricate these specimens, and few time dependent material properties we have taken. And this is the result. This is your melted area. This is the melt pulled boundary heat affected zone. You see this is the first track. Then again this here is second track. Then here you would be a third track. Similarly, we have done two layer in that case, and this is like we validated, like we have done the optical microscopic analysis of the ice printed specimen. In that case, we evaluated the melt pull, your melt pull depth and weight. So this is our experimental weight that we obtained. So 155 is the average weight in micron with the standard deviation of 8. And in simulation, we observe 160 micron with the standard deviation 6 weight, the depth. So weight basic, and this is your hatch spacing, especially between two melt pool. So this indicates your hatch spacing. So you see the result, the simulation result. So the accuracy within 10% error. Then some sort of phase analysis also has been done. In that case, like the material, the material undergoes phase change from solid to liquid pool and back to the solid material. And in this case, we have used the user-defined field subroutine code. So basically, this gray one shows your powder, and this shows your liquid, the combination of liquid melt and the solid. And this is my conclusion. So you see the spherical, it is in the powder in spherical with 30 micron, and the formation of gamma pressure take place with the heat treatment. And also endurance, there is improve in the endurance fatigue limit with the heat treatment. And the fourth point is like the crack has been inserted from the defects of porosity, lack of fusion. And you see FEI has been performed with Abacus for multi-track scan user, and user subroutine have been developed to model the heat source as well as the user-defined field. Thank you so much.
Thank you.